Hi, this is Varsha Radhakrishnan, and I'm going to present my project on comparative analysis of normalized cuts algorithm and k-means clustering for the network sciences course. We look at clustering and its application in today's world. It has a wide range of applications from computer science to statistics. One of the most traditional algorithms in clustering is the k-means clustering. Um, and the other form of clustering is the spectral clustering. Spectral clustering can be, there are various types of spectral clustering, and one of the types is normalized cuts or the Shih-Malik algorithm, which we see today. So MATLAB simulations will be performed in this project for a given set, and that implements both algorithms, and so that we compare techniques and identify clusters that are non-linearly separable in input space. A faster and more efficient form of k-means is explored and also implemented in MATLAB. So this project will lead to a qualitative conclusion that is derived from the results that we obtain. Firstly, we look into k-means clustering, where k in k-means refers to the number of clusters that we want. What happens in k-means clustering is that um, each the number of n number of points are divided into k clusters, and each cluster will be assigned a centroid. So the centroid will be placed in different locations so as to be as far away from each other as possible. So the next step entails taking each point in the data set and associating it to the nearest centroid. If n points are to be partitioned into k subsets, uh, then we see that the nth data point and the geometric the centroid of the data is S. So the strong point here is the ease of implementation of the algorithm, and it's just a simple re-estimation process, and it has many iterations are done and after initializing and until a stopping criterion is met. So the limitations we see here are quite plainly the differing density from, as we see here, from the original and the k-means cluster. The other limitation is the non-conformal shape or the non-globular shape. Um, and so spectral clustering is another form of clustering. It is a data technique that it makes use of a spectrum or eigenvalues of the similarity matrix of the given data to perform dimensionality reduction. The similarity matrix is a quantitative assessment of the similarity of the points in the data set, and the metric that we make use of in spectral clustering is the uh, graph distance. The similarity matrix is made sparse, and it requires the number of clusters to be specified. The technique works for a small number of clusters rather than a large number, and so one of the techniques used is the normalized cuts algorithm, which we see. So the normalized cuts can is a here the graph can be partitioned into two adjoint sets as seen in the formula, and by minimizing the cut we optimize the partition of the graph. Uh, and in the thing about the normalized clustering, the Shih-Malik um, algorithm is that it has so the Similarity matrix is computed and along with the W matrix, that is the weighted matrix. Next we compute the unnormalized Laplacian L, and if the so the cluster of the points is computed by performing the k-means algorithm, and so the cluster output will be from A1 to AK, the A and K being uh, the uh, the kth cluster. So we move on to see the simulation results in MATLAB for the NCUTs and the k-means. The data set that we use is the Zachary data set, and this, when translated into MATLAB, is a matrix that appears to be a 78 cross 3 matrix, and the value of k is what we take is equal to 2, and the output is obtained. Um, so the k-means clustering and the spectral clustering, as we will see, both perform the same task, both perform the same function, and we obtain the output in the plot. But even though they perform the same task, the spectral clustering is um, said to be superior. We will now see the implementation of the normalized cuts. This is the algorithm, the function of for the normalized cuts. So what happens here is we load the data set, the Zachary data set matrix, and the sparse matrix and the full matrices are computed, and the weighted matrix W1 and W2, are zero matrices are made, and the addition will form the weighted matrix W. We translate this into a graph to see the plot, and the ground truth values are taken, and this is the function call for the normalized spectral clustering. This function performs the simple task of the spectral clustering, where D is the diagonal matrix and L is the Laplacian matrix, which is the subtraction of the diagonal matrix and the weighted matrix. So this is the specific function of the Shih-Malik algorithm, where the Laplacian is calculated and the eigenvalues are formed, and finally the k-means of is taken, and that is given as the output, and we obtain the clusters 1 and 2. So when this is the graphical plot representation, and we see that the matrices are formed, and the values, the clusters are formed. Another implementation of the um, above can be said as the light k-means. The k-means is not very effective in MATLAB code, and the light k-means is more effective, and it is faster than the normal k-means. So this is our data set, and this is the cluster. These are the clusters that are formed. If we go back to light k-means, we will find that the code here is as vectorized as possible, and the inefficient k-means function i- is removed of its redundancies, and it's also 10 times faster, uh, and the output is obtained is grouped into two clusters here as well. The disadvantages of k-means we will see is that uh, the initial grouping will determine the cluster significantly when the number of data are not many, and we never know the real cluster. So it is using the same data. If it is inputted in a different way, it may produce different clusters for the same data. And the assumption is that each attribute has the same weight. We don't know which attribute contributes most to the grouping process. And to overcome these disadvantages, k-means is used only when there is a lot of data available. The ncuts also has its pros and cons. Uh, does not make strong assumptions, um, like the k-means, where the assumption is that the clusters are convex, and it is computationally more efficient. The cons are that it is very sensitive to the selection of the similarity matrix and parameters. Thank you very much.